All right, so we're going to move on to some specific polygons. Over the next series of classes, we'll start talking about quadrilaterals. Talked a lot about triangles already. The next step up would be quadrilaterals. Quadrilaterals having 4 sides, right? Also going to let you know that beginning now, you need to really get into your notes on a very regular basis, because we're going to have a lot of properties for a lot of different quadrilaterals that you're going to have to remember and be able to use. So you're going to want to study those a lot and know those very, very well. Okay? So first thing we're going to talk about are parallelograms. We're going to find angle and side measures in parallelograms. You need to know what a parallelogram is. Okay? Some key vocabulary there. Most of those you should already know. A parallelogram you may not. And so we get into that. The definition of a parallelogram. The word parallel is in there. So it shouldn't be too surprising that a parallelogram is a quadrilateral with both pairs of opposite sides parallel. So if we have this quadrilateral PQRS, if we know it's a parallelogram, then we know that automatically the opposite sides are parallel. So PQ and RS will be parallel, QR and PS will be parallel. And from those parallels, from this parallel property, we get a lot of the other properties. Specifically, well, if this side and this side are parallel, that means that they're always going to be the same distance away from each other, right? If they ever are not, if the distance between the two ever changes, that means that they're coming together and they're going to eventually touch. So the distance has to stay the same. And true for these guys here as well. So since that's the case, if this segment and this segment is designed to somehow represent, at least at some level, the distance between those two sides, they're going to be the same. And vice versa the other way. So what we get to here is theorem 8.3, which says that the opposite sides are congruent. Okay? So in a parallelogram, if we know that a quadrilateral is a parallelogram, then we know that the opposite sides are congruent. Right? No problem. Okay? The next theorem, I want to skip down a little bit into your notes, because I think we're a little out of order here. So I'm going to skip down. And just below that, to the right, there's a question in your notes that says, what do you remember about consecutive interior angles? All right, so I want to take you back to chapter 3, where we had 2 lines and a transversal. And if those 2 lines were parallel, we had, well, first of all, 2 lines and a transversal make all kinds of different angle relationships. If the 2 lines that are forming those relationships are parallel, then we know that those relationships have certain properties. Consecutive interior angles were these guys that made those C's, right? Do you remember what was true about your consecutive interior angles for parallel lines? Well, hopefully you're remembering that these were the only set of angles that were supplementary. The rest of them were congruent. And you can tell because this angle and this angle, no way are they the same measure. One looks obtuse and one looks acute, which is kind of cheating, but makes enough sense. Okay? All right. So if that's the case, then we look at, so they're going to add to 180. If we consider the fact that in a parallelogram, again, this side and this side are parallel, and consider this angle, so this side and this side are parallel, and consider this side to be a transversal, then we have that C here as well. Or to see it better, I guess, we know that both pair of opposite sides are parallel, so this side and this side, and this is a transversal. Then there are your consecutive interior angles here and here, and they're going to add to 180. They're going to be supplementary. You can go all the way around the parallelogram doing the same thing to eventually get to the point where we realize that if a quadrilateral is a parallelogram, then the consecutive angles are supplementary. Consecutive angles come from consecutive interior angles, or the angles that are sort of next to each other as you go through the shape. Okay, they're going to be supplementary. Okay? That's theorem 8.5. If we go back up to the theorem we just skipped, I'll show you this. If I know that angle P and angle Q are supplementary, and angle R and angle Q are supplementary, Then we go back to chapter 2 to a theorem that says that supplements of the same angle are congruent. That means that angle P and angle R are going to be congruent. And I can go through the same process for Q and S. Angle Q and angle S are going to be congruent, and I can prove it the same way. What that means for us, let's see if we go back up to this theorem 8.4, is that if a quadrilateral is a parallelogram, then the opposite angles are going to be congruent. So here, we would know that angle Q was congruent to angle S, and angle P was congruent to angle R. Okay? Automatically, if it's a parallelogram, those opposite angles are going to be congruent. Okay? Some examples for you. Here, ABCD is a parallelogram, and so we need to be able to find the value of x and y. Well, because this is a parallelogram, I know that the opposite sides are congruent from one of those previous theorems. So we just set x plus 4 equals 12, subtract 4, and x is going to be 8. I also know that the opposite angles are congruent, so y has to be 65 degrees. Right? As long as you know your properties, these become pretty easy. Example 2 and 3. Stop the video, come up with some values, start it back up, and see if you've gotten them right. Okay, what did you come up with? Again, this guy, FGHE, is a parallelogram, and we know that because these arrows are showing us that. Both pair of opposite sides are parallel, making it a parallelogram, or p-gram for short. Okay, if that's the case, opposite sides are congruent, so if HE is 8, FG is 8. And opposite angles are congruent, so if angle E is 60, angle G is going to be 60. Okay? At the same time with number 3. If it's a p-gram, and it is because these opposite sides are parallel, I know that this side and this side are going to be congruent. So y is 15. And I know that this angle and this angle are going to be congruent. So set those guys equal to each other. And x ends up being 25. Okay? All right. Let's see. We did this already. Right? We got to the fact that these consecutive angles are supplementary. Now, the last property here is that when you draw the diagonals in a parallelogram, those diagonals are going to bisect each other. Okay? So if we know that we're looking at a parallelogram, then we know that these diagonals are bisecting each other. Remember, bisect means cut in half. So we're creating some congruent pieces. QM is congruent to SM, so these guys are congruent. And PM is congruent to RM, so these guys are congruent. Now, QM and PM are not necessarily congruent. We don't want to go that way. Okay? The diagonals themselves are being cut in half, so those are the only congruent pieces. Now, to prove that, it wouldn't take much. Right? Because when we draw the diagonals in here, we do create 4 small triangles. And if I consider these 2 triangles here and here, right, I can prove those 2 triangles congruent. Remember some of our shortcuts. Vertical angles are always congruent. In a p-gram, opposite sides are congruent, so those sides of the triangles are going to be congruent to each other. And then we talked about parallel lines here and a transversal there. Well, that's not the only transversal in the picture. When you draw the diagonal in, you also get another transversal. This transversal and 2 lines are creating a Z, which are your opposite interior or alternate interior angles. So those alternate interior angles are going to be congruent. And so now by angle, side, these 2 triangles are congruent. And going back, still back to those congruent triangles chapter, because these 2 triangles are congruent, and this piece and this piece are corresponding sides of those triangles, then those 2 segments are going to be congruent. So I can put those tick marks there. And I can do the same thing with these 2. Right? They're corresponding parts of those 2 congruent triangles, and so they have to be congruent. Remember CP, CTC? So it's not too tough. We have to use congruent triangles to get to the part where those two diagonals bisect each other. But that's the proof. The theorem's good. We can use the theorem. So anytime we know that we're looking at a parallelogram, we know the diagonals bisect each other. So, some more quick examples for you here. Right, there's a desk lamp. And I know in your notes it's very, very tiny. But this desk lamp it's kind of on an arm. So you can raise and lower the desk lamp as you see fit for whatever purposes. And these desk lamps used to be made this way, and you can probably still find them, but where they've got two arms here, two arms here, and they create this parallelogram, both at the top and the bottom. Okay? This is a parallelogram, and then the angles are going to change as the lamp is raised and lowered. So what is the measure of angle BCD, which is right here, if the measure of angle ADC is 110 degrees? Well, if you look, this angle and this angle are consecutive angles, right? Parallel line, transversal, making a C, so they have to add to 180. So all you got to do is subtract 110 from 180 and find out that that angle is 70 degrees. Okay? All right. Another use for these theorems, right? Here's a standardized test question here. If you consider the diagonals in a parallelogram, so we can take a parallelogram and put it in the coordinate plane, just like this one LMNO was, draw the diagonals. The diagonals intersect at point P. How do we go find the coordinates at P? Well, one quick thing before we get into that. That symbol there is your parallelogram symbol. If you see sort of a slanted rectangle next to 4 letters, it's supposed to mean that it's a parallelogram. Okay? Well, how do we find the coordinates of P? We know the diagonals bisect each other, right? So since LP and PN are the same, that means P is the midpoint of that segment. And if P is the midpoint, then we can use the midpoint formula. The midpoint formula says that we just average the x's and average the y's to find the coordinates of the midpoint. Now, we have to have some points here. The coordinates for L are 1, 4. The coordinates for N are 6, 0. So now we can add the x's. 6 plus 1 divided by 2. And 4 plus 0 divided by 2. And 6 plus 1 is 7 over 2. 4 plus 0 is 4, divided by 2 is 2, and so we get to answer A. Okay, now you do have 4 answer choices. Of course, you can kind of just test taking skills, problem solve your way into the right answer too. I'll leave that for you to look at, but if you're ever in a situation where you don't have 4 answer choices, then you can still come up with the coordinates for the midpoint by just using the midpoint formula. Okay? All right. Another example here for you. I'm going to let you think about this and write in what you think the measures are. Just stop the video, come up with your answers, start it back up, and see if you're right. All right. So, NM. NM is part of a diagonal, this diagonal, which has been bisected. So if this is 2, that means NM is 2. And if these two pieces are 2, then KM is going to be 4. Angle JML is here, this angle right here. And I know that this angle is 110. So these two angles are consecutive angles, so therefore supplementary. So I'm going to take 180 minus 110, and that's going to tell me that angle JML is 70 degrees. And since angle JML is 70 and this angle right here is 30, then to find KML, which is the other side of that, we're just going to take 70 minus 30 and get 40. Okay? Hopefully you got to all of those. And that makes enough sense. If not, make sure you come in and see me. All right. Now, moving on. We just talked about the properties of parallelograms. Now we can flip those and start talking about how to show that a quadrilateral is a parallelogram. Okay? Proving parallelograms. All right? And again, same sort of set of vocabulary, and make sure that you understand those vocabulary terms. But here's the deal, right? So last section we knew that a quadrilateral was a parallelogram, and because we knew it was a parallelogram, it gave us all of these properties and then some, where the opposite sides were parallel and congruent, the opposite angles were congruent, the diagonals bisected each other, which is not shown here, and the consecutive angles were supplementary, which is also not shown here. Okay? Now, it's important to understand that in order to prove that a quadrilateral is a parallelogram, then we have to go the other way. We would have to know one of these properties in order to assume that our quadrilateral was a parallelogram. Okay, and again, not all the properties are shown here, but we're going to go through those. So it's all about what you know and what you'll know because of, what you'll learn or what you can conclude because of what you know. Okay, for example, and we're just going to sort of flip-flop some of these theorems. First of all, Theorem 8.7, which says that if both pairs of opposite sides are congruent, then the quadrilateral is a parallelogram. And it's important to understand that we have to know that both pair of opposite sides need to be congruent. There are other quadrilaterals that have one pair of opposite sides congruent, but they're not going to be quadrilaterals. So we've got to know both pairs. And same thing with the opposite angles. We've got to know that both pair of opposite angles are congruent, because there are some quadrilaterals that have one pair of opposite angles that are congruent and are not quadrilateral. So it's got to be both. But if we know that characteristic, then we know it's a p-gram. Okay? We can prove that it's a parallelogram. Okay? Same thing here. Now, Theorem 8.2, I'm going to skip 8.9 for a second. 8.10 says that if we know the diagonals bisect each other, then we know that the shape, that the quadrilateral is a parallelogram. Now, it is important to understand that both pair of diagonals need to be bisected, because there are quadrilaterals that have only one diagonal that's bisected. That's not going to be a parallelogram. So make sure that you understand that both diagonals have to be bisected. Now, Theorem 8.9 sort of merges two of these properties so that we only need to talk about one pair of opposite sides. But if one pair of opposite sides are both congruent and parallel, then we know that ABCD is going to be a parallelogram. Okay? So, do we have to know both pair of opposite sides are parallel and that both pair of opposite sides are congruent? No. We can use one side as long as they're both parallel and congruent. Okay? So, let's put these to use. In quadrilateral WXYZ, we know that the measure of angle W is 42, X is 138, and Y is 42. Okay? Go find the measure of angle Z. Well, if you don't remember that the angles have to add to 360 in a quadrilateral, you can always use the theorem n minus 2 times 180 to find that out. Okay, but they are going to have to add the 360. So we could do something like x plus 42 plus 42 plus 138 has to equal 360. And when we do, x is going to end up being 138. Now, does that make WXYZ a parallelogram? Well, if we were to draw this, WXYZ, remember how we name quadrilaterals? You got to start at one vertex and work your way around in order. So that's how the angles have to position themselves. Well, angle W and angle Y are congruent. Angle X and angle Z are congruent. So is this a parallelogram? Yes. Yes, it is. Why? because both pairs of opposite angles are congruent, and that makes this a parallelogram. Implies, that little double arrow means implies that this is a p-gram. Okay? So that's how we know. All right? Another example for you to think about here. What does X have to be in order for this quadrilateral CDEF to be a p-gram? Think about it. Come up with a value and stop the video, come up with the value, and then start it back up to see if you're right. Okay, did you come up with 2? Well, if this is going to be a p-gram, the diagonals have to bisect each other. So that means 5x minus 8 would have to be equal to 3x, and just solve that, and x ends up being 2. So 2 is the only value of x that would make this guy a parallelogram. Okay? Now, a couple more examples that are not in your notes, but so we can talk through pretty quickly. But amusement park rides, and you see this ride in those parking lot carnival type things, where you've got 2 swinging arms here and here, and a riding platform here, and it kind of rocks back and forth when it first starts getting going, and then eventually it starts just making this big old circle. Okay? Well, if that's the case, like I said, AD and BC are your swinging arms. And we know that DC always stays parallel to the ground. Okay? If that's the case, the moving platform AB, how is that always going to be parallel to the ground? And you would want it to be, otherwise people start falling out, right? So we don't want that. And you can see that as long as we construct AD and BC to be the same length, and we construct DC and AB to be the same length, then because opposite sides, both pairs of opposite sides are congruent, that means ABCD is going to be a parallelogram. Right? And if ABCD is a parallelogram, that means that AB and DC are parallel. Right? And we already know that DC and the ground are parallel. So by that transitive property of parallel lines, the platform is always going to be parallel to the ground. Okay? Using the properties of p-grams. Okay? Another use here in London, there's this doorway, there's a building that has kind of just started leaning over time. So how would we know for sure that SV and TU are the same length? If you're looking at that, because ST and VU are both parallel and congruent, that means that VSTU is a parallelogram, and that means that both pairs of opposite sides are congruent. So that's how we're going to know that SV and TU are the same length. Okay, so a couple of uses for these parallelograms. Okay, now to summarize, right? How do we prove that a quadrilateral is a parallelogram? Well, we can show both pairs of opposite sides are parallel. That's from the definition. We can show both pairs of opposite sides are congruent. We can show both pairs of opposite angles are congruent. And that would make our quadrilateral a parallelogram. Or we can show one pair of opposite sides are congruent and parallel, and that would work. Or we can show the diagonals bisect each other. Now, one thing that is a property of parallelograms that we have not talked about was the fact that, let's see if I can't get this in, another bullet point here, but that your consecutive angles are supplementary. Now, you'd have to show that a couple of pairs of consecutive angles were supplementary. But you could get it done if you ever needed to. That's one property that we're not really talking about here. It's kind of the hidden property. We're not going to do that very often because it's pretty tough to show that angles are supplementary. But it is there, and it is possible. Okay? All right. A few more examples here for you. So 5, 6, and 7, what theorem can you use to show that the quadrilateral is a parallelogram? Right? Stop the video real quick, give it a shot, start it back up and see if you picked out the right theorem. My guess is you probably will. Okay, number 5. Oh, number 5. What theorem can we use? I don't know what the number is, but the one that says that one pair of opposite sides are congruent and parallel, and that would prove that this is a parallelogram. Number 6, the theorem that says that both pair of opposite sides are congruent would work. And number 7, the one that says that both pairs of opposite angles are congruent would work. Or, like I said before, you could show that these consecutive angles are supplementary and these consecutive angles are supplementary, which is kind of a long way of showing that the opposite angles are congruent, but you could do that as well. Okay? But both pairs at number 6, if you wanted to say what theorem you were using, you would say both pairs of opposite sides are congruent, says this is a parallelogram. And number 7, you'd say that both pair of opposite angles are congruent, means that this is a parallelogram. Okay? And last but not least, this example here. For what value of x is going to make MNPQ a parallelogram? Well, again, we're talking about diagonals, and the diagonals need to bisect each other. So in order for this to be a parallelogram, these two expressions would need to be equal to each other. And so x would have to be 2. Okay? So that's showing that a quadrilateral is a parallelogram. All right? So that's it. Those are your properties for a parallelogram. Next time we'll start adding different shapes and their properties as well. Okay? Homework's out in Canvas. Make sure you get that done.